Welcome to our first SCL IRC seminar of the year. We would like to welcome Professor Brian German, who happens to be a triple jacket with bachelor's, master's, and PhD from Georgia Tech, and director of the relatively new Center for Urban and Regional Air Mobility. I got it right, did I?
You did.
Did, very good. And Brian's been a wonderful colleague as Georgia Tech becomes more and more interdisciplinary, and we have more interdisciplinary centers. We're starting to see more and more overlap and opportunities for engagement where freight, people mobility, energy all intersect, and it'd be a great discussion today, I think. And as usual, we'll allow Brian to let you know whether he'll take questions throughout or hold to the end. And Brian, we hold the time till 1:30, and different people do it differently. If you want to stop, 10, 15 minutes before the end and then do questions, if you could let the audience know whether you're available afterwards if you want to talk, that type of thing. And so please join me in welcoming Professor Brian German.
Thank you, Tim. So I'm really excited to be here. I got to know Tim in the Supply Chain Logistics Institute just a few months ago in the process of building this Center for Urban and Regional Air Mobility. I'll tell you a little bit about that at the end of the talk, but I want to first bring you up to speed on why this is exciting, at least in my opinion right now. Short story, we're sort of poised in the aerospace community to have a transformation happen. And it has to do with recharacterizing what it means to fly. As simple as that. We think of going to the airport and flying 500 miles, right? Well, what if you took an aircraft and flew 25 miles? That's sort of interesting, flying 25 miles instead of 500, and what would that look like and why? And you can just imagine that's an entirely new market for aviation, for people, and for cargo. And so you'll recognize that there's a lot of OR and logistics problems in this space as we start to redefine aviation. So that's the overall context, and I'm going to talk a little bit about why this is happening from an aircraft technology standpoint too. And one of the key reasons is electrification of transportation. It's happening in the automobile, and it's now happening in the aircraft. So that's why we're at the point we are. So let's start with a sort of brief history of electric flight. Did anyone know when the first electric airplane flew? It's not on this chart, it's earlier than this. Anyone know? It was in the 70s. Someone did it as kind of a stunt. It was a lead acid battery. It was like a washing machine motor, right? And they made something fly. I haven't listed it here. I need to update my slide, but that happened. But really, the history of modern electric flight began because of these things, right? It began because of what was happening in consumer electronics. So you look at the Apple Newton there from 1993, when we were looking at NiCad batteries replacing lead acid, and ultimately nickel metal hydride batteries came along. This was pre-lithium ion, right? The things that we have now are lithium ion. So we had these PDAs which were really pushing the technology for high specific energy to give enough talk time on your device. Now, people have been flying little radio-controlled airplanes for many years, and at some point, that battery technology combined with motor technology and what was going on in controls engineering, the ability to make a brushless DC motor, very reliable, very effective, those two technologies intersected, and suddenly all the hobbyists are flying around these little fixed-wing airplanes. Now, you guys probably know that that has extended to go beyond little fixed-wing airplanes into the quadcopters. You might own one, you might fly it around campus, right? So all this was happening really starting heavily in the early 2000s. The military picked it up, and then came 2007, the Apple iPhone, right? Apple put a big investment in lithium-ion technology, and really we've been moving forward in that direction. 2008, Tesla. Tesla said, hey, we can make an all-battery electric car, right? Not like the Prius, which was hybrid electric and had an engine and a small battery system that was nickel metal hydride, but rather we could have a fully electric car with a battery system that's lithium ion. So that was a big deal. 2011, NASA sponsored something called the Green Flight Challenge, which was basically to ask how much efficiency, equivalent efficiency, could you get out of an airplane. So a company called Pipistrel in Slovenia modified one of their gliders with an electric propulsion system and blew away the competition with some amazing numbers like 400 miles per gallon equivalent, right? Which was pretty striking. The drones I mentioned, you see in 2013, we really started seeing quadcopters everywhere. 2015, that same company that made the airplane, the glider airplane, was positioned to actually market a product. So they built a flight trainer that they called the Pipistrel Alpha Electro. You can buy one of these now. You can fly it in the European Union, and now very recently we're getting authorization to fly those in the US. Full electric powertrain, lithium-ion batteries. NASA is looking at this technology now very heavily, and one of the neat things about electric is suddenly having this big internal combustion motor that had to be in one place and turn a propeller. We don't have that problem anymore. We can distribute propulsion around the airframe because these motors are very highly power dense and they maintain that power density as we decrease their size. So suddenly I can fragment the propulsion system, put thrust where there's drag, and get favorable aerodynamic interactions. Okay, so this is all happening, a lot of neat stuff. You might ask, why electric? Well, in the context of the electrification of transportation, you're probably aware of the reasons. Same things for airplanes as for other vehicles. One is that they're quote unquote greener, right? We take the problem of CO2 emissions and other dangerous emissions off of the vehicle. Now that doesn't mean that we don't have those problems anymore. It just simply transfers the problems to the terrestrial grid, right? So now, okay, and you know what, frankly, that's okay for me because I know we can do things at scale there and more efficiently thermodynamically. Okay, so there's some good reason to do that. But by the way, we need to be a little bit cautious because when we look at the life cycle carbon, we need to consider the manufacturing of the aircraft. We need to consider that batteries don't last very long and they have to be replaced and they have rare earth metals in them. Okay, so this stuff is just now coming up. I mentioned distributed propulsion with NASA's interest. It's mechanically simpler, aerodynamic advantages, so that's exciting. The other thing is low noise. If you've ever been to a general aviation airport where you have small airplanes, you'll have in your mind that distinctive character of sound of a piston aviation engine. I love the sound, but it could be annoying to a lot of people. And it's a problem for airports that operate a lot of airplanes, right? So lower noise because of electric, and most importantly, most profoundly, lower cost in pretty much all aspects. Lower cost of acquisition, the capital cost of buying the aircraft, lower cost of operations because now I source power from the electrical grid at say 11 cents per kilowatt hour as opposed to $7 a gallon for leaded aviation gasoline. Yes, it still has lead in it, right? Not the big jets, but the little airplanes, okay? And so there's just a lot of cost advantages. The other one's maintenance cost. An electric motor has very few moving parts, really, just a sort of really single moving part. And so it's a lot simpler. It vibrates less. That means it does less damage to other parts of the airplane, and the maintenance costs come way down. Okay, so I showed you, hey, this is happening. There's a lot of sort of small efforts, things that don't look like they'll change the world out there, right, from that previous slide. But look what else is happening. There's a rise of something that's called eVTOL, is the acronym, eVTOL. That stands for Electric Vertical Takeoff and Landing. VTOL, vertical takeoff and landing, is an old aerospace term for things like helicopters, right? But also crazy things that they tried in the 1950s, having jet engines mounted up and down that would directly lift you off the ground, things that would tilt, right? Lots of configurations that would give you vertical takeoff capability. Turns out all those things they tried were immensely mechanically complex and failure prone, and effectively none of those were successful other than the helicopter, except for, anyone know which one we use now? A vertical takeoff and landing aircraft has something that tilts. F-35 is fair. Okay, so I stand corrected 2 things. F-30, maybe 3. The Harrier, stand corrected. I was thinking the V-22. So there's about 3 of them, right? The V-22, Osprey, the Harrier jump jet, and the F-35, right? So there's a few. But now here comes electric, and the entire game has changed. Nobody knows how to do it. And so what you see on this slide is a few companies that are trying a lot of different things. Here's 6 images of different prototype aircraft that are flying. The top left is a company called Volocopter in Germany, and it's basically a giant multicopter, right? You see a quadcopter or hexacopter flying around campus. Just imagine you put 18 of those rotors out there, and you've got a Volocopter. The one in the middle is a company founded by Larry Page, actually. Larry Page being the co-founder of Google. He's wanted to do this stuff for a long time. This is called the Z-Aero Cora, and you see it's a multicopter. It's got a whole lot of those little rotors, but it's got a wing in the middle. And the wing gives you forward flight efficiency. A lot of rotors gives you hover efficiency, but if you want to go far and go fast, you need a wing, and so that's why they're looking at that configuration. Airbus Vahana, top right, tilt wing. Both of those, the front wing and the back wing tilt, and that gives you some aerodynamic advantages. The Joby S4 on the lower left is a tilt rotor. It has, in this rendition, I think it's 12 rotors. The new version has 6. Each one of those tilts independently of the wing. Aurora Flight Sciences is a company that was actually acquired by Boeing for their work in this area, and they have a configuration that's now becoming called Lift Plus Cruise. You have a whole series of lifting rotors on those 2 pods on the side, and then you have a pusher propeller on the back of the airplane. And lastly, you have this company called Lilium out of Germany on the bottom right, which the entire duct, it's a ducted system, and the ducts, the trailing edge of the wings tilt, okay? Now, for some context, here's 6 examples. One of the professional societies in aerospace is called the American Helicopter Society. I should say it was called the American Helicopter Society. They've now rebranded themselves as the Vertical Flight Society, largely because of what's happening in this space. And they're tracking over 200 prototype aircraft of eVTOL aircraft in development worldwide. Now, some of these admittedly are just people in their garage, but many of them are now increasingly large aerospace companies, well-funded startups, et cetera. And I'm showing some of the levels of investment here. So this is happening, and it's really exciting. Now, you might say, why? Why would people be interested in an aircraft like this? Well, they're targeting a market that's becoming known as urban air mobility, which is given the acronym UAM. So urban air mobility, the name says it all, right? It's flight in cities. It's an air service that operates in cities. So think about an aerial taxi that might carry you as a passenger from somewhere in Atlanta down to the airport. That would be a mission in urban air mobility. And what really launched this field is that Uber said they're interested in 2017. And they started an initiative called Uber Elevate. And these 2 images are from the Uber Elevate white paper, and it really sums it up. So if you look at the image on the right, you see a parking deck in a city. On the rooftop of the parking deck, there's a lot of these aircraft and parking stalls. There's a couple of big squares that have an H listed on them. That's the landing area for the aircraft. And then you see the aircraft. It's one of these novel eVTOLs with a lot of different rotors. The other thing going on is that's in a city, right? It's in a place where we wouldn't normally have aviation. So you can think about the challenges from a policy standpoint, from a land use standpoint and regulatory standpoint. There's a lot of complexities embodied in that image. The image on the left is what you would see as a rider, as a consumer of this service, and that's your cell phone app, your Uber cell phone app. So Uber wants you to be able to book an Uber Air trip, just like you can book an Uber X trip or Uber Pool, or maybe better yet, a multimodal service where an Uber car takes you to a vertiport, as these things are being called. You get on the aircraft, you fly to another location, and then you do last mile in an Uber car again, right? So a full journey. So there's a pretty exciting kind of thing that I think for those of you who work in mobility, you recognize the many challenges of doing that on demand, managing the fleet, managing the crew, the pilots. There's a lot of difficulty and opportunity there. And so what's different about this UAM compared to other forms of aviation? And you might have detected already that the answer is basically everything is different, right? The user experience is different, right? We could have passenger air taxis. And oh, by the way, I didn't really talk about the cargo side, but a lot of these aircraft are being envisioned for carrying freight, for carrying cargo, packages that have certain urgent delivery needs to them. I wish I would have put the slide in here that showed some of those specific cargo aircraft, because this is the Supply Chain and Logistics Institute after all. But there's quite a few novel configurations specifically tailored for cargo. Same overall technology though. Okay, the aircraft technology is different. There's the electrification aspect. There's also the flight control aspect, which is really hard. And then there's the aspects of autonomy, going even farther than flight control, of could we get rid of the pilot? That's what people want to do in the long run to really further bring down the operating costs. Operations and infrastructure. How do we manage the infrastructure, the land use issues, the public policy pieces, the airspace management, right? If we imagine how the FAA manages airspace in the US now, one controller, one flight controller typically handles about 20 airplanes. We now imagine a world where there are tens of thousands of flights above any given major city around the world at a time. We're not going to hire an extra 500, 5,000 flight controllers, right? We're going to automatically manage airspace and handle the dispatch problem. Okay, so this is another piece of research that's being worked. So kind of channeling those things, why is UAM difficult? The electrical technology, battery technology, it's still not quite there, right? So people are working on this metric that is specific energy, the amount of energy per unit mass of the box that is the battery, pushing that number higher, pushing the volumetric density higher as well. Simplifying flight, we talked about autonomy, things like that. The other aspect is, even if we can't go to full autonomy, right? Even if we still have pilots, there's a massive pilot shortage right now. We can't find enough pilots to fly commercial aircraft around the world. So companies are scrambling to train them and to get them prepared. So one idea that has been put forward is what's called simplified vehicle operations. The idea that maybe we could make the aircraft simpler to fly, we automate the inner loops of flight control, and we automate increasing numbers of those, but we always maintain the most difficult part of situational awareness and perception and assign that to the human. Okay, that's an entirely different paradigm of flying aircraft, and we don't know how to do that yet, and we especially don't know how to get the FAA and other regulatory agencies to approve anything we put forward. Okay, so that's a big area that's getting worked. Manufacturing. Let's say we want to build tens of thousands of these aircraft per year. That's actually sort of happening in people's planning processes now to meet demand. Well, tens of thousands of aircraft per year is a very different scale than aviation. If you look at Boeing, Boeing builds hundreds of aircraft per year, and it's a different scale than automotive, where they build hundreds of thousands to millions of units per year. So it's somewhere in the middle, right? Composite airframes that are difficult to manufacture. We need to build 10,000 a year. Nobody knows how to do it. The aerospace manufacturers say we'll scale up. And interestingly, the automotive manufacturers are entering the market and saying we'll scale down our rate of production and we'll be able to address the market in that way. Does anybody follow the news of the Consumer Electronics Show? Do you ever look in this time of January to see what kind of exciting new electronic gizmos are going to show up in Las Vegas? That just happened about a week ago, and a big news splash announcement is Hyundai, the car company, has founded an urban air mobility division, and they're going to build an aircraft for Uber. They showed a picture of it. I wish I had it. It's got rotors everywhere. But they are going to leverage their manufacturing strengths to this market. Noise is a big problem. Even though these things are expected to be quieter than helicopters, helicopters have a lot of noise challenges to get public acceptance. There's a lot of detailed work on aerodynamics and on acoustics to really allow us to design these aircraft for low noise. Okay, so where might we operate these aircraft? Because initially they'll be very short range, maybe less than 60-mile maximum range. That's not very far. You're not flying between cities. So you're probably going to identify markets where there's a lot of population density and where you can be very competitive against ground transportation modes in an economic sense, right? And so I looked at a map of the US from the Census Bureau that shows urbanized areas. And the urbanized areas are indicated by the purple dots here. Now I just circled, some of the biggest urbanized areas in the US with 50-mile range diameter circles. Okay, and you can start to see that, hey, maybe I start to get somewhere there. I can start to address a lot of urban areas in the US with a 50-mile range. But as you're very well aware, every city is different. Its shape is different. Its morphology of where people live is different. The population, the spatial population distributions, the geography, the terrain, if there's mountains, if there's rivers, if there's a bay, all these things are different. And now imagine where I would place that infrastructure, which is going to be largely new, in order to serve the potential demand and even to generate the demand for the service, right? Remembering now that these aircraft have a limited range and they need time to recharge between flights. Batteries are not instantaneously recharged. It takes minutes, maybe hours to recharge batteries. So if you want to get operational tempo up, you're very concerned about that. So there's a lot of challenges about the city and which of these aircraft is better for which types of cities. And one of the reasons, and by the way, which type of service too. What's your vision of how this service ought to operate, right? Will you allow a stop in the middle where you can pick up more people? Will you not? Is it a scheduled service? Is it an on-demand service? Is it somewhere in between? All these are open questions, and depending on your answers to those questions, because batteries are so energetically fragile right now, you get a different aircraft. And that's why we saw on that earlier slide, we don't have a dominant aircraft configuration yet. So the key points here that I would make are right now, we don't know, as an aerospace person, I'm an airplane design person by training, I want somebody to tell me the requirements for the aircraft, right? And that's old school military language of here's what the aircraft must do for us to buy it. We love that as engineers because then we can just check the boxes, but nobody has done that yet. And so there's a big effort to understand and discover the requirements, even at the highest level. Payload, range, speed. Those are the main things we need to know. And those things are going to vary city per city and service type to service type. Correspondingly, we don't know the aircraft configuration, as I said earlier, because that's going to depend on those requirements. And lastly, another important part is we don't even really know the physics, how to model the physics for these new aircraft properly, especially in the early phases where we're making trade-off decisions based on these requirements, right? When we're trying to get in the right ballpark. Eventually, I can hire 80 engineers or 100 engineers and tell them, design that vehicle, work on it in great detail, and we'll get a good solution. But to even figure out what's the right vehicle to work on is a big challenge because of issues like the noise, the aerodynamics, and the battery performance. Okay, so that's a background on kind of what's happening in this field. I want to introduce you to a little bit about what I've been doing in my group and some very rich collaborations that we have going on here at Georgia Tech. And as part of this, I also want to just make you aware of it and let you know that in this new center we've formed, we're trying to build momentum and interest at Georgia Tech to put together teams to go after these problems, right? So that's kind of my ulterior motive in giving this talk, by the way. But some of the things I want to tell you about is work that I've done on looking at eVTOL performance modeling, and this was done with Uber and funded by NASA subsequently. A little bit of work on lithium-ion battery modeling at the right level of abstraction for the trade-offs with requirements that we're working on now. And lastly, just to touch on some operations research type problems that I've been doing in my group and in collaboration with others to really envision the operation, and by doing that to envision to determine what the requirements would be. And this last category of the operations research element is one area in particular that I think we need a lot more emphasis. Okay, so I did a study in 2017 for Uber, which was looking at basically they asked the following question. What is the level of battery-specific energy, okay, that we need to make these things work for our trial market, which is going to be the Dallas-Fort Worth area? That was their question. And they gave us some requirements and said, go for it. I did this work in collaboration with Rob McDonald, who was at the time a professor at Cal Poly, and has since decided, you know what, I kind of don't want to be an academic anymore. I'll go to work with Uber doing this stuff. So Rob's doing some neat work. There's a video of this that's like an hour long if you wanted to go see our entire presentation. It was at a summit that they held called the first Uber Elevate Summit. Basically, what we did is we started, and all aircraft studies start with a mission, right? What's the purpose of the aircraft? It's almost always go from point A to point B, but there's a lot of detail in between. For a vertical takeoff and landing aircraft, you have to hover for a while, then you climb, and then you cruise like, forward flight, and you reverse that to land. It's important when you consider how much battery you need on the aircraft that you also envision the possibility that maybe something goes wrong and I actually need a little bit of extra energy, right? I need a reserve of energy. So there's a reserve requirement, which you see here is an additional hover, an aborted landing, and we take off again and we divert to another vertiport 2 nautical miles away and we land again with a hover. Okay, so that's for sizing and planning purposes. You have to make sure the aircraft can do this from a safety standpoint, but you know that in nominal operations, the aircraft will almost never use that much energy. The aircraft will almost always hover for a shorter amount of time, fly for a shorter distance, etc. But you have to make sure you can do it. And so this defines the notion of what we would call a sizing range, or a maximum distance for the aircraft, and a nominal mission range. And what you're seeing here, there's a lot of details on this slide, but the takeaway is Uber did analysis of their own data in the Dallas area, and they have the benefit of having a lot of data, right? Because they carry people around Dallas anyway. And so they know where people want to go, origins and destinations of their trips. And they determined from that a 55-mile maximum distance would be acceptable, but the nominal trip would be 24 nautical miles. I'm sorry, this is actually statute miles, 24 statute miles, okay? And on the right, you see a plot that is the distribution of flight distances in a network that they were envisioning at the time. Okay, so that's kind of our starting point. And we modeled a whole series of aircraft configurations, these novel eVTOLs. You see a few of them here. Everything from a single main rotor helicopter, coaxial helicopter, to a whole lot of hybrid configurations. And here I don't mean energy hybrid, but what I mean is propulsion hybrid. So some that have tilting wings, some that have tilting rotors, right? Different configurations. For each one of those configurations, we did some analysis, we did some literature search to establish ranges of potential more fundamental aerodynamic or propulsive performance characteristics. So, for example, how much lift to drag ratio could we get out of these aircraft? Turns out that's the predominant impact on efficiency in forward flight, the ratio of lift to drag. Typically, a Boeing 747 might have a lift to drag ratio on the order of 18. Okay, 18, that's pretty good. Sailplanes could have a lift to drag ratio of 50. A multicopter, if you fly a quadcopter, has a lift to drag ratio, if you're lucky, of like 2. Okay, so that gives you a sense of what we're talking about in terms of the efficiency in forward flight. Now there's some people who say we can get an OAD of 5 out of a quadcopter, so we'll see. But we presumed ranges of these values because knowing that different engineers would design solutions that are novel and could have different trade-offs of these parameters. The other one is disk loading. Disk loading is the measure of efficiency in hover. And it's basically a simple idea. It's the amount of weight carried per unit area swept by rotating blades, okay? The higher that number, the higher the disk loading, the less efficient the aircraft is in hover. Okay, so for each one of these, we have a series of these values, and from that, we can immediately derive the requirements for power in hover and power in cruise. And power is just one step removed from energy, right? Because if I take power, multiply it by the time it's in cruise or the time it's in hover, now I have the cumulative energy requirements for that mission. So that's why we can look at it this way. And each one of these configurations, I can look at power required in cruise versus lift to drag ratio and power required in hover versus disk loading, right? Each one has a particular place. And I could co-plot those if I wanted to, as you see here, where cruise power is the x-axis, hover power is the y-axis.
Sorry, go ahead.
And each one of these little bubbles, colored bubbles, indicates the sort of range of variability we might expect for each one of those canonical concepts based on the designer's approach to synthesizing the aircraft, right? So those little bubbles become a kind of basin of typical capability for those aircraft. And what do we want? Well, we want aircraft that have really low hover power and low cruise power, okay, ultimately. So we want to be as far to the bottom left of this plot as possible. This is kind of a Pareto frontier, by the way, if you recognize that term, a multi-objective optimization problem. If I minimize both of those things, that's in general good. But when I then specify a particular mission, a particular amount of time in hover versus a particular distance or time in cruise, then one of these is probably going to be a winner. And so, with data like that and knowing our mission, we can actually overlay, you'll see these contour lines of battery-specific energy. So we're looking at 100 watt-hours per kilogram versus 400 in various places here. Let's just see if I can bring up a laser pointer and show you, right? So here's a 200 watt-hour per kilogram, 400 and 600 line. By the way, batteries right now battery packs for aviation are almost 200 watt-hours per kilogram. And we really need, we want more. We want 300. We always want more. And so with that kind of information, we did a sizing study. And basically the concept of sizing an aircraft, to introduce a term to you, is a good friend of mine in industry says the question is how biggy, weight, how wingy, wing area, how thrusty, how much engine do you need? And basically, this was mass sizing to figure out to carry 4 people, okay, and go a certain distance, how much battery do I need and how much aircraft gross weight do I need? And so I'm going to skip the details of this plot, but other than to say we presumed a baseline of 300 watt-hours per kilogram specific energy, and we presumed a baseline 5,000-pound vehicle, which gave us a nominal range for each one of these aircraft. This sort of said, at the near-term levels of technology, what could we get out of a multi-copter, an autogyro, a helicopter, et cetera? And then now let's look at sensitivities where we say, all right, let's change the weight, or let's look at the variability in its lift-to-drag ratio or its disk loading and sort of see what the implied changes to specific energy are. And what we learned from this study is that these aircraft want to be heavier than a traditional internal combustion engine aircraft. We have to have a lower so-called payload fraction. Less of the vehicle is payload, more of the vehicle is battery, right? And that's how you get the longer range. But that means the aircraft is being heavier, is going to have a higher capital cost potentially. So you start to see the character of some of these trade-offs. The other thing we did is a very careful accounting of how much energy each mission segment required. And a key bit of this is that for safety reasons, we're just never going to access a certain fraction of the battery's capacity. And the reasons are reserve, one, we only fly reserve in an emergency situation, but also there's margin that we apply to protect the battery. If you take a lithium-ion battery and you start discharging it and you get to the very end, have you ever looked at your cell phone when you get below about 20%, it just falls off like a rock, or your laptop? Same kind of thing can happen to airplanes, because what's happening is the voltage is dropping, I have to hold power, and I've got to increase the current flow, and that's a faster drawdown of the capacity of the charge. So this really strongly coupled effect means that I really need to make sure I never use the last 20% of the battery. And I may not even want to use the first 10%, because if you notice when you charge your phone, that it charges pretty quickly, except for the last few percent, right? The last 5% takes forever to charge. It's because the battery had to go from a constant current to a constant voltage charge mode, and it charges slower. Now imagine you're operating a service where you want to have high rate of operations. You're not going to tolerate charging that last 10% perhaps. Okay, so that's unused energy. That's just dead weight we carry around, inaccessible energy. So it's only a portion of that's accessible, and that portion changes with distance, right? So as I fly the aircraft at a different distance. Different aircraft have different characters of these types of plots showing how the energy is used. One of which I'll highlight to you here is, look at this thing called a tilt duct, okay? This one has an enormous amount of unused energy because its hover efficiency is so poor. Okay, so the result is that I can have notice that this stacked bar chart doesn't even go past 10 miles of range, because that's all we can get out of it with this battery type, considering the need for all these reserves. And similarly, look how much the energy is consumed by those reserves, and particularly in hover. Okay, so we see the different character of these concepts coming out, and yet if I change those requirements, I'd get different answers. We can look at now battery performance of recharging. Let's presume I recharge after each landing. So these zigzag plots are plots of the battery state of charge. You can think of it as how much fuel is in the tank, right? This is a fuel gauge plot. Versus time of day in operation, okay? So you start out at the beginning here. Maybe this is, I forgot where we normalized it. This must be, let's say 6 a.m., right? So the x equals 0, time equals 0 location, let's say is 6 a.m. You fly a flight and the battery discharges. So you have that negative slope. Then you land and you recharge it, the dashed line moving upward. And then we didn't fully recharge it. Look, we don't have to do that. Uber said, hey, just charge for 5 minutes, but charge at some ridiculous power like 300 kilowatts. There's some new technology that might let them do that. So you charge for 5 minutes, put a little bit of energy in, you fly again, you deplete that energy, charge again, etc. Now eventually, what's interesting is, let's say you're flying this nominal mission, 24 miles. Let's say if I wanted to fly that repeatedly, just repeated back-to-back 24-mile missions, what we'd find out is eventually I'd use up that buffer at the beginning, and then I'd have to charge longer than 5 minutes in order to safely dispatch the next mission, right? Because I have to protect my reserve and all that. So there's some interesting character of how much charging time you need based on sort of sprints that you might fly during a day. During rush hour, I might be okay with flying with a net decrease in battery charge, knowing that that initial buffer would let me get in more flights in a fixed amount of time. So you can just sort of see all the operations research questions that are kind of emerging here.
Quick question.
Yeah.
Is there potential for swapping batteries?
The potential for swapping batteries. It's a good question, and I'm gonna have one slide on that at the end of the talk, where we've modeled that as a job shop scheduling problem, where you schedule batteries into chargers, and you have an inventory of spare batteries, and you have an inventory of chargers, and you try to bring down the cumulative cost, considering full life cycle net present value type costs, including capital costs. I think it's a really interesting idea. We've interviewed aviation mechanics about this and other people, and there's a lot of practical concerns. For one, these things are immensely heavy. So imagine you have a 5,000-pound aircraft and you're taking out a 3,000-pound battery pack. That's an enormous undertaking, specialized equipment. It's not people removing them. And it turns out that the connectors are very fragile and fatigue easily. So just very fundamental stuff about the plugs is a little bit of an issue here. But I think it's an idea that people have talked about, and there's need for more work in. Now I want to talk a little bit about how we model batteries, and this is a little bit change in direction. I'm going to go quickly through this, but I think it's important to understand. You know, I come from a background in aviation, fuel-burning aircraft, where it's a pretty simple idea. I have so-and-so amount of fuel in the tank, and I can get that energy out up to whatever I can't access with a pump that's in the very bottom of the tank, right? But with a battery, the interesting thing is the amount of cumulative energy that I get out of it depends upon the rate at which I ask for it, right? So the profile of power delivered over time affects the cumulative energy we get out. And if I really draw down increase the power a lot and draw all that energy with high power, the battery's going to heat up, and it's going to dissipate a lot of the energy it contains as heat. So there's a lot of losses associated with pulling a lot of power out of the battery. So there's a trade-off here, and we need to be able to model that in a way that lets us understand the impact on the aircraft performance. And it turns out battery models, there's all sorts of battery models. There's the electrochemists, right, so who work on constitutive models and ordinary differential equation, actually partial differential equation models based on detailed descriptions of the battery design. The anode, the cathode, the separator, all the details there. Those are challenging. They run rather slowly. And you need to know a lot of information to deal with them. There's equivalent circuit models. If you're a controls engineer, you probably work with equivalent circuit models where you make everything look like capacitors and resistors and inductors that change as a function of state of charge, okay? And they build models that are very useful, and they're actually used to develop battery control systems. Okay, so there's that category models. But what we're interested in now is something more abstract, a higher abstraction model, where you don't need to know as much information and that can be used in early conceptual studies and operations research studies. So we've leveraged a series of empirical discharge models based on a paper by Shepard in 1965 that have been modified over the years, and that's what we used in this Uber study. And we sort of developed our own way of modeling these. And it's based on these curves, these empirical curves. And this is what, if you buy a battery, you get a data sheet. And the data sheet tells you the cell voltage is a function of the capacity discharged, right? And so you see it drops. As I discharge the battery, the amount of voltage it's providing is going down. And as I increase the current I ask for out of the battery, the voltage goes down. That's the different curves on this plot, different currents. Higher currents have lower voltage delivered to the load, okay? So there's a lot of interesting things going on in here, and this is data for this cell that we used in that NASA electric airplane that they're actually going to fly out in NASA Armstrong later this year. So this is data from that cell, and if we apply some best practices like we talked about earlier, like maybe I don't fully charge the battery because I don't have time to, and I certainly don't let the battery discharge below the last few percent for safety, I trim that data and I say my operational range of state of charge of the battery is narrower. When I look at these curves, I say, wow, those are pretty close to linear, right? It's like a multilinear kind of thing. And indeed, you look at multiple lithium-ion cells, most of them have that character. So we developed a really simple model, discharge model, empirical, that has some physical basis to it, so I might call it semi-empirical, where you model the voltage U is equal to some open circuit voltage U0 minus some K times the discharge capacity, that's the x-axis value is Q, okay, minus the internal resistance, R times I is the current, the internal resistance R is the amount of heat that we're going to dissipate ultimately as I draw down the battery at higher powers. And then there's an interaction term, right? The slopes of those lines change as a function of current and the capacity. So that simple model does a pretty good job, and here you see a curve fit of that. Now, for those of you who are work in stats or would rather make a more complicated emulator model, you can do better than this simple linear model. But I love the physical insights. I love that we can extract a measure of the internal resistance and calibrate that. That data is usually provided by the battery manufacturer, the internal resistance. So there's a lot of physical insight to it. And we get a pretty good overall fit model. And so we've used models like that remember this is a constant current model. We can turn that into a constant power discharge model, and I'll skip the details. But a very good model can be developed in that approach by simply a little bit of algebraic machination, one additional linearization which has small effect. And the result is we get a nice model. And to skip the equations, let me tell you what we could do with it. Here's the canonical problems of airplane energetic usage, right? One, you might ask the question, if I have basically a certain amount of energy, let's see, let me see if I can get which problem is which here to make sure I say it right. First is find the amount of energy that can be delivered when the battery goes from a state of charge level Q1 to a state of charge level Q2. Here's the example for a car or something like that. When the fuel gauge reads 3/4 of a tank to when the fuel gauge reads 1/4 of a tank, how much range could I get in that distance of the fuel gauge? That's the top problem. The second problem is, let's say I have a final capacity. I want to find the final capacity after delivering amount of energy at a given initial capacity at a specified power. That's basically, I started at 3/4 of a tank. I want to drive 20 miles. Now what's the tank read? What's the gauge read, right? Maybe it's half tank, right? That's basically it. And the last one is kind of the inverse problem. This is really useful in the airplane design process, which is to find the initial charge required to fly with a given amount of required energy at a given power and a given final capacity, right? So I want to land with the tank not empty. I want to land and there's still some fuel in the tank and I wanted to fly this far. What did the gauge need to read before I took off? This is the dispatch problem. We don't dispatch the aircraft unless that happens, okay? So with this model, we can do a lot of cool stuff, including this is just showing the cumulative energy delivered by the battery as a function of the ending state of charge, where we start at the same initial state of charge, and each of these curves correspond to different levels of power. And what we see is that the highest power delivery curve results in the least cumulative energy delivered, right? So it's dissipated more heat, and we've basically lost that energy to use in the vehicle. So this is a really rich problem that if you think about it from how that connects to operations, it's a first order effect. It's not a second order effect. So I want to change gears a little bit now and talk a bit more about the operations research type work that we've done in my group and in collaboration with others at Georgia Tech. And I'm a little bit, shy, embarrassed to present our work in this area to this crowd because that's what you guys probably have a lot of strength in. So please don't laugh me out of the room. But I'm excited by it, and I think there's a lot of neat things that can be done. Now, we wanted to work on finding requirements, right? So what is the range requirement for the vehicle? How far do you really need to fly these things to serve a particular business model? And so NASA asked us to do this study, and they wanted us to model several cities, Los Angeles and San Francisco in particular, and basically they said, hey, is there anything you could do with census data? Look at where people live, look at where people work, look at their income levels perhaps, determine their willingness to pay and their willingness to fly these aircraft versus to drive a car based on time savings, and then figure out where you'd put the infrastructure on the ground, the new vertiports, and then figure out what the distances are between those vertiports. Okay, so that's the path that we started, and I'll say that we're just I'll show you some of our initial work in that area. One of the problems we solved was the problem of so-called vertiport placement. Where would you put these takeoff and landing pads? And this is a map here where you see a lot of the segmentation of the map here is census tracts. So those of you who've worked with GIS systems, the census tracts are what we're looking at, and this is San Francisco Bay Area. And we brought in an API to like Bing Maps or Google Maps API, so you get turn-by-turn driving directions, and you get drive times as function of time of day in traffic, right? So now we can look at okay, first mile, last mile. Let's presume people drove to the vertiport and then drive from the vertiport for their first and last mile. So we can say, let's imagine a point I want to put on the map, and it's that magenta dot. Okay, let's now draw a 5-minute catchment zone around that magenta dot. And that's the drive time catchment zone. If people were willing to drive for 5 minutes, how much of the map could you cover to get them to that vertiport? And so that's the green area you see surrounding this magenta dot. And so the problem we solved was, and then a certain portion of the people, okay, that live in, or work in the area shown by the magenta, or shown by the green plot, have an income at a level which might make them willing to fly these aircraft. Okay, so there's a sort of threshold income, and we just at this point presumed a market share estimate, okay, of those people to say maybe 5% of those people fly, something like that. There's a lot more work that can be done in that area, as you can imagine. So basically then the problem is an integer programming problem, because each one of these tracks can either have a vertiport or not have a vertiport. You move around, you say I want to place 10 vertiports, you simultaneously move around 10 of those magenta dots until knowing what the origins and destinations of the people are in terms of home and work, thinking about commuting, by placing those 10 vertiports, we generate the maximum number of trips. Okay? That's the problem that we solved. And this is kind of how it looks. This is now LA area. And you see the top row is 10 vertiports, then 20, then 40. I want to call your attention to what happened. And the vertiports themselves, by the way, are the tiny little blue dots on the left figures, and the purple lines are the lines connecting those vertiports. You probably can't tell it, but the thickness of those lines is connected to is proportional to the implied demand for that OD pair. Okay, so basically, what's interesting in LA is traffic is so terrible in LA that if you could place 10 vertiports, your best thing to do is place it right around LAX and right around downtown, and you'd still generate a lot of demand. Now, as I increase the number of vertiports I'm willing to place, we open up that network and we see some more distant routes begin, and then we go to 40 vertiports, even more so. Okay, so that was kind of interesting. And then here's where kind of coming back to what I'm interested in my primary research area.
Did you assume a given capacity for the vertical?
We did not. We did not look at capacity. This is unconstrained by capacity. That's a huge question. So when you think about aerospace management, everybody realizes that vertiport capacity is going to be the bottleneck on this whole thing. If you're going to fly tens of thousands of flights per day, that's really hard to schedule these things into the vertiports and from an aerospace standpoint. Yeah. But what we derived from that was distributions of trip distances. Okay, so remember in the Uber study I showed you a CDF of those distances? Same thing here. We wanted to be able to do that looking at a different number of vertiports in different cities. And we would compute, you know, the mean, the 50th percentile, and then we'd also compute sort of something close to the max, the 95th percentile trip distance. And for 10 vertiports in LA, again, it's really short, 11.8 miles mean distance and 15.8 miles maximum. And what's interesting is that is considering competition with cars, right? That's considering competition with cars and a penalty for wait time at the vertiports. Okay, so that is telling you the potential about, really what it's telling you is how bad traffic is in LA, right? That's the big thing it's telling you. The other piece of this puzzle is doing something other than just picking a market share out of thin air, but really doing some work on demand. And fundamentally, you might ask I'm collaborating in this topic with Professor Laurie Garrow in civil engineering, and she's an expert in transportation demand modeling, specific focus in aviation. So she's done a lot of work in aviation, and she's really one of the leaders in getting into this urban air mobility space in terms of demand. And she titled a paper, you'll see that sort of second paper on the right there, first paper on the right, titled, "If You Fly It, Will Commuters Come? Predicting Demand for eVTOL Urban Air Trips." And that's really the question we're asking: at what value, what cost, what ticket price, and at what level of time savings would you prefer to fly as opposed to drive? So to get to the bottom of that, because this is a new market, we don't have existing data to look at, Professor Garrow has set up big nationwide surveys, nationwide at least 5 cities in the US, 5 major cities where we've had maybe 2,500 respondents in each of these surveys. The first one looking at just kind of current day, where you compare and contrast with driving a personally owned automobile or an Uber rideshare. And the second, bringing in autonomous ground transportation, right? If you're going to predict the future about flying, what about predict the future about driving too, to make it a more fair comparison? So, you know, these surveys are basically structured as choice models, if you know how that works. And here's an example on the right. You know, would you prefer to take this car if the cost is $5 and the travel time is 40 minutes? Or would you prefer to take this aircraft where the cost is $10, flight time's 15 minutes, there's an ingress-egress time of 20 minutes, and you know, do you have a guaranteed ride home? So there's a lot of effort to construct these surveys in a way that you get meaningful data, and that's really pretty challenging to get people to say what they're going to do. But that's been very useful, so we've been collaborating on that to build multinomial logic models to then feed into these other types of operations models we're working on. And just another example of work that we're doing, this is the battery swap example that was asked about. And we've just put in a paper on this where we've looked at now regional aircraft, not the aircraft flying in cities, but slightly longer range, fixed wing aircraft, more traditional looking airplanes. The example we looked at was actually Mokulele Airlines in Hawaii. They fly a lot of really, really short routes between the islands in Hawaii. And the potential for them to save money with electrification is enormous. So we were studying that problem, and we asked the question, well, what if you could swap the batteries? And you'd have extra batteries, and you'd have chargers. So what you do is schedule batteries into chargers. And the key idea is as follows. It turns out that you pay for electricity not just based on the cumulative amount of energy you get out of the wall when you plug it in, but again, the rate at which you ask for it. How big is the plug, right? If it's a 120 volt plug, that's one thing. If it's a 240 volt, you're going to pay more from the power company. If it's a 1 kilovolt, you're going to pay an enormous bit because they had to plumb the whole system. They had to get the cabling to you, and you're going to pay per month for that. So what if you could do peak shaving such that you could basically bring down your cost of electricity on average? Maybe then it would justify the logistics problem of managing these extra batteries, buying extra chargers, and charge them slowly overnight. So we looked at that problem and modeled it as job shop scheduling, and we showed some pretty considerable benefits in terms of net present value. That paper is under review. I hope it's going to get accepted soon, so when it does, I'll be happy to share that around if anybody's interested. And just a few more slides. The last 1 or 2 things I wanted to mention is that we love to build airplanes if you're in the aerospace department. Our students love to build airplanes. It's a lot of fun. This is an exciting time to be an undergraduate student in aerospace, or a graduate student for that matter. You want to go work for one of these many eVTOL companies. So we're doing some of that where we build a subscale airplane, we fly it, we work on the control algorithms and things like that. So we built a subscale tilt rotor aircraft. You see that those back 2 rotors tilt, become propellers in forward flight. We just did it because we could. It was fun. Been doing things like that. The students here on the left, one of my favorite photos here, they won a competition based on their work on that. We're also designing and building novel short takeoff and landing aircraft. This is a aircraft with a 10-foot wingspan, 6 propellers, 3 on each wing semispan. So it's a blown wing configuration. By blowing the propeller slipstream over the wing, we augment the lift of the wing at low speed, so we can get incredible short takeoff and landing performance, where this aircraft, we haven't yet flown it, but it's going to happen in February, can probably take off in 2 body lengths of the aircraft. Okay, so that's really pretty exciting. And so, you know, these are some of the things you can do with electric propulsion, reimagine the airplane, basically. So in this big context of here's electric flight, here's urban air mobility, one thing that I realized early on is that this this field is a lot bigger than my own little research area. You know, I'm an airplane design person. I'm interested in performance modeling, things like that. But I've gotten kind of drawn into this OR side because that's where the funding has been, things like that. But it's really occurred to me the problem's bigger than me, and we really need a lot of other people engaged on different parts of the problem, and we need to go after big proposals and try to do fun stuff together in teams. So we formed the Georgia Tech Center for Urban and Regional Air Mobility. We've been socializing this idea across campus, connecting with people like Tim and Benoit on this topic to see what we can do together to really solve some big problems where we're doing things like working on vehicle technology. Okay, here on the left you see aircraft technology research. That's a bundle of work where you can just imagine Georgia Tech engaging across the board. Everything from the people in electrochemistry and battery design to people working in mechanical engineering on high power density motors to people working in electrical engineering on high power density electric drives, right? Aerospace people doing integration on vehicles and thinking about aerodynamics. That's all really cool stuff. But then there's the other whole half of the problem that is operations. It's the public policy piece of it. It's the economics modeling piece of it. All these things are of huge interest because companies are pouring billions of dollars into this field, and frankly, nobody knows anything about the answers there on the right-hand side. There's so much uncertainty on how we build the airplane on the left-hand side, the aircraft technology, but I think that pales in comparison to the questions on the right-hand side of this plot. Okay, so we formed this center to work in this direction. We had a kickoff meeting in January of last year, and we sort of framed it as a local problem too. We said, hey, if you're going to do research in urban air mobility, you need a lab that is an urban area, right? So we're situated in Atlanta. Why not engage the local community to see what we can do? Maybe we could have some test ranges. Maybe we could gather data from MARTA and other places, right? So a lot of potential for that. So we had a co-sponsorship between the Metro Atlanta Chamber of Commerce, the Georgia Chamber of Commerce, and the Georgia Centers of Innovation. So that was a really nice event. We had about 100 attendees. We had a national panel of speakers from Uber and other places talk about UAM and the opportunities. We're currently working on a lot of proposals and thinking about how we can go after federal funding on this, particularly for multiple investigators. So if you're a faculty member, you're interested in this area, I'd love to talk with you about it, figure out how we can write something big for NSF, that kind of thing. We have an interesting collaboration going on now with University of Georgia and Emory University on rural healthcare applications of drones, and not just drones, but bigger aircraft. What could we do, and could we do something kind of cool in Georgia to compete with what other states like North Carolina are doing? Many of you may have heard of, anyone here in North Carolina's work? Drone delivery in North Carolina is a big thing now. They're taking a leadership position. So I think the question is, could we do that here in Georgia? And lastly, we're exploring collaborations with Hartsfield-Jackson International Airport in this topic area. Tim and I attended a meeting looking at could we do something with them. So just a quick summary of where we are. And that's my last slide. I've said a lot, so I think we have a little more time. I'll be happy to open it up to any questions. Thanks a lot. Yes, sir.
There's this big problem of disposing the batteries. So like, have you thought about anything regarding
At end of life, after they're, yeah. So that's a great question. You know, batteries. When I sort of got into this field only about 5 years ago, I didn't realize what a complex system a battery cell is, right? But it's got chemistry, it's got mechanics going on, right? You actually have basically flow of atoms across these one-dimensional layers, and there's fatigue and cracking and degradation that happens. So they wear out, short story, and when they wear out, they often get potentially unsafe. There's a lot of things that happen. So people have proposed, well, one of the things that implies is that after maybe 3,000 cycles, that's kind of about where we are now, these things may be unusable. Maybe they've degraded such that 20% of their initial capacity is gone. So you need to replace them. There's a lot of open questions about even how and when to replace them. Do you do it as part of a nominal aircraft inspection cycle, or is it a special event? And then what happens to the batteries afterwards? I think that's what you're asking. One idea that people have talked about is, hey, well, if I'm going to have a lot of these aircraft flying around to these vertiports and recharging, well, what if I took the used batteries and put them on the ground and used them as a power bank on the ground to continue, there it's not as critical, right? But to continue to be recharged and to then peak shaving from the grid and then charge the aircraft out of that battery bank. That's one idea. Otherwise, I think it's just the same character of problem we see in automotive and other places where there's a lot of clever ideas, but at the end of the day, nobody has any great answers. And we kind of just hopefully figure out how to recycle them so we could at least get the cobalt out of them. But open question. Yeah.
There was some great insight on the topic as well. I had one opportunity with my friend. I was and he was booking an Uber from New York to Manhattan. And he was getting a Uber cost of $55 for a cab. And guess what? How much he was getting for Ubercopter?
Good question. What was he getting?
51.
51.
Yeah.
So 55 on ground, 51 with Ubercopter. Yeah.
So I think it's getting momentum across,
Yeah.
but what my concern is more about the air traffic in the zones, and
Yep.
just like airports have a control tower over there, are vertiports also having such control mechanisms just to control the air traffic? Because I think that's a point of concern over there.
Just a great question. So first let me address your comment about your friend at the beginning. I thought that was really neat. Cheaper for Ubercopter than on ground. That's probably because they're taking a loss on purpose to test the market. That's probably what that is. But you know, just to give you a sense of the numbers that people are talking about, let's say $5 to $7 to $8 per passenger mile right now is what people are thinking about. Okay, that's a lot of money, by the way. But that's to help calibrate it. That's the target for once we get these eVTOLs in the fleet and we get them operating. In the near term, that might be where we are. Now, the second question you had about what's happening about airspace management at the vertiports and you don't have air traffic controllers, that kind of thing. Also open question. NASA has a project that they've established, you know, at their headquarters level to study this. It's called ATMX. And they're looking at several different paradigms, one of which is based on doing what they're envisioning to do for drones, right? So you have the package delivery drones and you imagine those operating. Well, the scale of operations there is much higher than what we're talking about for carrying people, right? It's maybe tens of thousands, hundreds of thousands of flights per day. NASA has a program called UTM, Unmanned Air System Traffic Management, so it's a compound acronym. UTM, and they're using an automated dispatch approach. So basically it has a sort of a federated approach where you could have different service providers that interface with a database that manages the airspace to avoid conflicts, but each one of the service providers can kind of sell a slot. And it's a first come, first serve thing on selling that slot. And what is that slot? That's a four-dimensional trajectory from origin to destination with some associated buffering and guarantees. So there's a lot of work, though, to figure that out, particularly when something goes wrong and when you have to catch up if you're not operating the way you should. So open question, but it's intended to be autonomous as an air traffic control system as well. Yeah.
For the Uber idea, would they own the aircraft as opposed to the cars? Like right now, the drivers use their own car, but then for the aircraft.
For the aircraft, it would probably be fleet owned, right? So been some uncertainty on what that business model would look like. Earlier, it was unclear if, think about Uber getting into this, if Uber would service the airline and buy the aircraft or just the connection to the consumer and somebody else owned the aircraft. The recent announcement by Hyundai about their entry into this market at CES, or actually it was Joby Aviation. Joby's another company. Joby signed an agreement with Uber where they would own the aircraft and they would operate the aircraft. So Joby would really be the airline and Uber would work on the vertiport infrastructure, the air traffic management, and the connection to the consumer with your app.
So then the vertiports would need the space to store all of these aircraft?
Good question. Mostly the vertiports are places just to embark and disembark passengers, right? The aircraft will probably be landed and stored at some other central facility or distributed facilities, yeah. Yes, sir.
Are you considering any other type of energy sources such
renewable?
So other types of energy sources. There's a lot of people who are interested in hybrid. They just don't believe batteries have what it takes. And so, can you take a gas turbine that's, downsized a little bit and operates very efficiently for the cruise condition, and we augment its power with batteries? That's a type of hybrid scheme that's been envisioned. There's a few companies working with fuel cells that they believe can actually provide the power density you need. Solar is interesting. Generally, what people have found on these kind of applications is solar doesn't buy its way on, if you will. In other words, the amount of incipient solar radiation you get per unit surface area on the airplane is not enough. And then you have the cloudy day issues, you have the maintenance issues, and now I have this other widget on there that has to work, but I can't really count on it. And so solar has not been preferred. Yep.
How do you approach the issue of cybersecurity? Because like for the next 10 years, we might have big problems with those technologies.
It's a great point. Cybersecurity is a big deal. There's a lot of talk about that in this space, and it's not my area, I don't really know where it stands, but I know people are, even on battery management systems, right? If you could mess around with the controller that is the battery management systems, you could take one of these cells and enter it into thermal runaway, in which case you could blow up the battery. So that's a big deal, and so people are talking about voting systems and, all of these data fusion approaches to controls people would know about to detect, hey, that sensor is probably bad, maybe that thing has been hacked.
Because the conversation is already happening around autonomous vehicles on the streets.
Yeah.
So imagine in the air.
Exactly.
There's a fleet of airplanes and
Yep.
they control them.
Scary, right?
Some, from the other side of the world.
It's a good research topic.
Yeah.
Yes, sir.
In terms of the vehicle technology and actually having a plane and a power source, like in your opinion, how far away are we from that? Of actually having something that's credible?
As an aircraft?
As an aircraft apart from all the public policy and all those other issues.
Yeah, so these prototype aircraft are flying, but to fly a prototype, sort of the companies, you might ask why they do that. Well, it's part of a development cycle where they're trying to build an aircraft that will meet the actual requirements. But it's also for press and to generate funding for them and things like that. And so these aircraft, the prototypes, don't fly the range we would need. They're much shorter range right now. They, generally speaking, are probably not capable of being certified by the FAA, which means the safety threshold that needs to be met is not there. It's not that it's not there, but it's that certification is a process by which you prove that it's there, that certification. That said, the era of prototyping has been going on for about 3 years now. This company, Joby, is rumored to be far ahead, and they signed a contract with Uber to initiate operations in Dallas in 2023. So I don't know if that means they'll have a fully certificated aircraft in 2023 or if they'll have an experimental class aircraft that'll fly some trial flights. It's a little bit unclear. The certification process is a potentially $billion problem per aircraft or more. That's potentially, say, 5 years per aircraft.
I think you also touched on this, but I'm wondering who will pilot the vehicles? I think so. At least initially, I can imagine some trained pilot would have to pilot us around.
Yep.
But I can imagine that adds to the cost as well.
Yep.
But then, is it possible then to get to a point where like I can jump out of my car without any training and then just jump into an aircraft like this? Can you design control systems that can do that?
Yeah, great question. Initially, companies are talking about helicopter pilots. So in the very early days, you bring in a trained helicopter pilot, cross-train them into these aircraft. Now, helicopters are very unstable. You have to have a lot of piloting skill. Even the earliest versions of these aircraft will have some kind of an automatic control system to take a lot of the pilot workload down. But they're still envisioning trained pilots. As you go forward, there's this idea of simplified vehicle operations where increasingly you automate systems, and that if you can convince the FAA, you can then reduce the pilot training requirements. So instead of spending hundreds of hours and thousands of dollars in flight training, maybe someone more closely to coming just off the street, with a limited amount of training could fly, and then maybe eventually you get to where you could be in the aircraft and provide some high-level with some basic training, safety assurances, and then ultimately fully autonomous. It's very speculative as we get farther out as to what will happen when.
I think we've run out of our regular time, but Ryan, are you available to talk with folks at all?
Yeah, I'm happy to stay about another 5 minutes. Then I got to get to the airport in a little while, but I'm happy to stay and chat a little more if anyone's interested.
Okay, please join me in thanking Ryan, and if you do have some questions.